Okay, so good afternoon, everyone. Welcome to the IMA Data Science Seminar. I think this is going to be the last seminar of this semester. Today, we are very happy to have Dr. Denny Wu from Quran Institute at NYU to speak in our seminar. So Denny is now a faculty fellow at NYU Center for Data Science. Before that, he got his PhD from University of Toronto this spring. His research focus is mainly on deep learning theory and high-dimensional statistics. Today, he's going to talk about learning in presence of low-dimensional structures, abstract random matrix perspective. Thanks, Denny, for joining us.
All right. Thanks, Yulong. Thanks for the introduction, and thanks for the invitation. I really wanted to come in person, but for this semester, I have teaching duties. So, and I'm going to Europe next week, so the universities might not be very happy if I take two consecutive weeks off. So I decided to do this online. So I think I have about 1 hour. So I'd be happy to take questions anytime during the talk or after the talk. But if there's anything that you want to ask, please stop me anytime during the at any point. Okay. So I want to briefly go over some of the research we did on learning in learning under high-dimensional asymptotic setting, and in particular focusing on two-layer neural network. This is joint work with my advisors, Jimmy and Murat, my PhD advisors, and Ali Raza at University of Toronto, Taiji at University of Tokyo, Zhichao at UCSD, and Greg at now at XAI. So I'll be primarily focusing on two papers at NeurIPS this year, which would be a follow-up. They're kind of like they're building upon one paper we did 1 year ago. So let me briefly introduce the problem setting first. So it seems to be a folklore that real-world data is usually high-dimensional, but then there's going to be some low-dimensional structure in it. Okay, and so like high-dimensional means that the number of input features for the real-world data set can be quite large. But then the low dimensionality is that there will be two aspects of it. The first aspect is that the target function might only look at a very small subset of your input features. So in deep learning theory, one way to model this kind of low dimensional target function is just to consider a single index target. Okay, so this is the ground truth. The function actually only depends on one direction of the of your feature. So in order to learn this F star, you need to find the right direction. This is the right one-dimensional projection. You also have to learn this unknown nonlinear function. Okay, so these are the two. So this is sort of a canonical example of a very low-dimensional target function. You can think of this as one neuron in a two-layer neural network. There's also another perspective, which is that the features, the input features, while they have high dimensionality, but they might also have some low-dimensional structure already. Right? So the covariance is usually not identity. There's usually some rapid eigendecay. So the data itself can have low intrinsic dimensionality already. And the simple way to model this would be one way to model this would be to consider spike covariance data. Okay, so my input features are drawn from Gaussian with a covariance sigma. And now sigma, instead of treating it as just identity, this has been assumed in various prior works. I'll go into more details about that. We're going to add one additional low-rank perturbation. Okay, and the magnitude of this low-rank, this is going to be a rank 1 term. This magnitude theta is going to scale with the dimensionality. Okay. So in other words, so the high dimensionality just means that the number of features will be very large, but then the low dimensional structure is captured by this low rank component. And if I have a larger theta, that means the data become more anisotropic. And so the intrinsic dimensionality intuitively is going to become smaller. Okay. So this is the setting that we're looking at. And the theta, sometimes I also refer to as the signal to noise ratio. So because this mu would usually would have some correlation with the ground truth, the target function that you're trying to learn. So large data also means that there's also more signal in your input features. Okay. So the way we're gonna, so this spike covariance model data, this assumption is kind of motivated by this spike random matrix models, which is a classical way to model some high-dimensional data, but with some hidden low-dimensional signal. Okay, so if you look at the eigenvalues of the covariance matrix that have the spike structure, then what you're going to see is that there's going to be a bunch of eigenvalues that are not very informative. So they correspond to this isotropic portion of your features. So these are referred to as the bulk eigenvalues. But then there will also be some low rank, due to the low rank perturbation, there will be some informative spikes, this kind of eigenvalues that pops out. And these corresponding eigenvectors contain the information of the ground truth. So this is the random matrix model. Okay, let me first briefly introduce the problem setting. So we are interested in learning a two-layer neural network and learning kernel model under this setting. So for learning at training time, we're just going to do empirical risk minimization. So we minimize the squared loss, and then the losses potentially, we might add an L2 regularization. So for kernel, we look at kernel ridge regression. Okay, and at test time, we look at the prediction risk, which is just the population L2 error. Okay, so this is this measures how well your model is doing at test data. And at least for the first half of the talk, we're going to look at the proportional asymptotic limit. So remember, we have n training examples for ERM, and we have D input features. So the proportional asymptotic limit is taking both of them to infinity, but we're keeping the ratio to be a fixed constant. So this is a classical way to model like very high-dimensional data. So this regime excludes the case where n is much greater than d. So you have this large data regime where you have a lot of training example. Instead, so the number of training example actually grows with the dimensionality of the problem. So this, for example, this will be able to capture over-parameterization. Right? So it's possible that if this ratio is small, meaning that there's actually more features than number of training example, then effectively I'm in the over-parameterized regime. So the more important reason for considering this asymptotic limit is that if we make very strong assumptions on the input data, which we already did, as you see, we assumed the input is Gaussian was a spike covariance, then we can actually compute the precise prediction risk for certain machine learning models. So, our goal is to decide if some so f star target function can be efficiently learned under this proportional scaling. Okay, so by efficiently learned, what I mean is the following. So if an algorithm can learn f star in the proportional regime, well, that just means that intuitively that means that I can achieve arbitrarily small prediction risk in using linear sample complexity. Okay, so there exists some ratio gamma such that when this gamma star such that when you have more samples than that, then the learning algorithm is going to achieve epsilon, at most epsilon population prediction risk. Okay, and the probability goes to 1 as ND go to infinity jointly. So this is intuitively, just think of this as so if an algorithm learns f star in the proportional regime, that just means that you can achieve you can learn this function with linear sample complexity. So does that make sense?
So Danny, I just want to clarify this. So D is the dimension of the input, right? It's not the
yes.
Of a neural network.
Not the number of parameters. Yes. So so for the one neuron case, so for the target function, D is also the number of parameters. Yes, but for the neural network, this will not. Yeah. Okay. Thanks. Okay, so let's look at the two models that we're considering. Oh, by the way, so I think in the literature, this kind of setting is sometimes called the student-teacher setting. So the target function is referred to as the teacher model, and the student is whatever the model I'm training. Okay, so I'm sometimes I'll use this notion. I refer to the kernel and neural network as the pseudo model. Okay, so we're going to consider two different models. One is kernel regression. Okay, so there can actually be two candidates. So we can look at random feature. Okay, so consider that this is kind of like a two-layer neural network, but the first layer is randomly initialized. So W0 is just randomly drawn from Gaussian or sphere, and then I'm fixing it, and I'm only learning the top layer. Okay, so this is, when the width of this random feature model becomes very large, then I get then this random feature kernel is going to concentrate at some rotation invariant kernel. So we are going to restrict ourselves to an inner product kernel. So so here we can also do kernel ridge regression. So the kernel is given as such, and the kernel ridge regression estimator also has a convenient closed form. Okay, so you would just invert this n by n kernel matrix. Okay, so these are the two models that. So by the way, one reason that so these in the high-dimensional asymptotics, in the literature of these high-dimensional asymptotics analysis, these two models are actually very popular in the sense that in the past few years, there's been a lot of work studying the precise training and test performance of these two models. Well, usually assuming the data is Gaussian and or the weights are Gaussian. So, for example, if you've seen like the double descent trend, so as a number of parameters or the number of samples increases, the test error can go down and up and down. So it's non-monotonic. A lot of these studies are looking at the random feature model or the kernel ridge regression model. Okay, so the punchline here is that for these models, because I only train the coefficient on top of my embedding, on top of my, so we can call these this phi as the features of the model. Okay, so there's no feature learning, so the representation do not change. They're sort of fixed at random initialization, and then whereas for neural network, if you think of this random feature, this feature map, if you think of this as defining a two-layer neural network, then if you train the first layer W, then intuitively you would learn the features in some ways that could improve the performance of the algorithm. So for the second class of student model, we are going to look at two-layer neural network where we actually train both layers. Okay. So intuitively, this should do better than the random feature or the kernel model where you fix it's like you fix the first layer. So for the two-layer neural network, so this is how we parameterize the model. There are capital N neurons, okay, and for each neuron, I have a weight vector W, okay, and some bias B, and then there's some nonlinearities sigma that applies entry-wise, and then there's some second layer AI, okay. Pictorially, so given some input X, so this neural network have some intermediate or sometimes referred to as a hidden representation, which is what you have after the nonlinearity of the first hidden layer, and then you collapse this hidden representation into one output scalar. Okay, so in other words, there are three sets of trainable parameters. There's W, the first layer weight matrix. There's A, the second layer, and there's the bias units B. Okay. This is not very important, but a side remark is that so now for the previously we have N and D, the number of samples, the number of input features. Now we have an additional variable, capital N. Right. So when we take the proportional asymptotic limit for convenience, we're also going to let the width of the neural network to go to infinity at the same rate as the other two variables. Okay, so if you just naively count the number of parameters in this neural network, then we're already in the over-parameterized regime because the number of parameters will be something like D squared. Okay, okay. So we're trying to learn this model by gradient descent. Okay? And the observation here is that given a convex loss, so most of the common loss function that we use for training will be convex, then if I only train the second layer, if I fix the first layer, then this is a convex problem. Okay? This is just doing linear regression on some feature. Whereas if I try to optimize the first layer, then this would not be convex even if I fix the second layer because of this nonlinearity sigma. Okay. So this is the more challenging. This is a more challenging part to analyze. But at the same time, if you optimize so as previously mentioned, optimizing the first layer W is precisely what gives you the power of representation learning, right? So intuitively, we know that the target function f star is a single index model. It only focuses on one direction. So the hope is that if you train the first layer W via gradient descent, then well, perhaps the first layer can find this low dimensional direction, this beta star. So then you can perform much better than a random feature model where this W is fixed to be like IID Gaussian. Okay. So how do we train this? So how do we implement the gradient descent algorithm? So for the sake of theoretical analysis, we're going to make a rather extreme simplification. We're actually going to take only one gradient step on the first layer. So the hope is that perhaps even after one gradient step, the first layer parameter W already contains some useful information of the target function. Okay, so this is there's some empirical evidence that if you look at the kernel defined by like the neural Hendron kernel, etc., then these defined by the neural network feature, they seem to change most rapidly in the first few iterations. So the first few steps seems to be we can we can wave our hands and say that this is the place where feature learning might have a very big impact. Just formally, so what we're going to do is for the first layer, we take one gradient step. Okay, with learning rate eta. And the gradient is just computed with respect to the empirical risk. And after that, the representation has changed a bit, and then we can learn the second layer, which is because it's a convex problem. So learning the second layer with the squared error and L2 regularization just give you the ridge regression solution. Okay. So essentially, we're doing the random feature ridge regression, but now the feature is not random anymore. The features has been updated for one step. So this is the training algorithm. And the intuition is that because we have, so for the single index target that we wish to learn, there are two components. We have to learn the direction, beta star, and the nonlinearity, sigma star. Okay, so the hope here is that the gradient descent step on W finds the direction for you. And then learning the second layer, it's via ridge regression, that's going to give you the nonlinear link function sigma star. Okay, so these are the two algorithms. Okay, so let's look at some prior results. So remember, we consider the case where the data have a spike covariance. So and the spike magnitude is controlled by this scalar theta. So when theta is 0, then that means my data is just isotropic. It's just Gaussian with identity covariance. So this is a setting that has been studied extensively studied in the past few years. So let's look at kernel models first. So if the data is isotropic, then there's been quite a few works showing that kernel models don't work very well in this proportional asymptotic limit, in the sense that for the performance, the prediction risk of the random feature model or the kernel ridge regression model can be lower bounded by this quantity. Okay, and what is this quantity? Well, this is a projection. This projects your target function f star to any degree polynomial that's with degree greater than 1. Okay, so in other words, so think of this as so for a given function, I can decompose it into a constant part, a linear part, and whatever that's beyond linear. Okay, and this p greater than 1 f star just means that I'm taking this part out. Okay, and the L2 norm of this nonlinear component of f star is actually a lower bound on the prediction risk of these the kernel models. So this means that in the proportional regime, kernel methods can only learn linear functions. Okay, if the data is isotropic. So if you look at these double descent figures, if we we can plot this dashed black line. This is a lower bound, and this lower bound is actually achieved by directly doing linear regression on the input. Okay, because it learns the linear part of the target function, and the random feature, the nonlinear kernel model, the nonlinear random feature model cannot outperform linear regression on the directly doing linear regression on the input data. Okay, so basically, if the data is isotropic, then yeah, it's a bad idea to use kernel models or a random feature model if you're trying to learn anything that's nonlinear. Okay. Okay, so what about neural networks? So the prior results, have shown that neural network can indeed, if you train the first layer representation, you can indeed learn a nonlinear target function. Okay, so but crucially, we need this thing, this condition. For now, I'm going to refer to as a non-degeneracy condition, which looks like the following. So I'm going to require the derivative, the expected derivative of my, so sigma is the nonlinearity of my neural network, and sigma star is the link function of the link function that I'm trying to learn. Okay, this is the target function. I'm going to assume both of them has non-vanishing first derivative, with the expectation taken with respect to a Gaussian. Okay, so in the next few slides, I'll explain why this is important. But if you, so this assumption is not really, it's not a big deal, because this is satisfied for any monotone activation function, right? So if a monotone function will not have, would have a non-vanishing first derivative. So ReLU, 10H, most of the activation we use is going to satisfy this. But then the sigma star is something I don't know a priori. So this assumption is something we cannot verify. But if you assume the target function have this property, then if you give me linear, if you give me n training examples and scale with the input dimension linearly, then the two-layer neural network can learn a nonlinear target function. Okay, so this is actually you can think of this as as demonstrating the benefit of feature learning, representation learning, right? Because for kernel models, if you don't train the representation, you can only learn linear functions. And here, under this additional assumptions, well, now you can learn a nonlinear single index model. Okay, and so last year the prior work that we did is we can also characterize. So we take one gradient step on the first layer, and we can characterize how the step size, the learning rate, affects the learning of this single index function. Okay, so this I will not go into details, but the intuition of why this happens, so why just gradient descent for one step, one gradient descent step already gives you a separation from kernel methods, is the following. So remember at initialization, my weights W are like random, that they're drawn from isotropic Gaussian. So the eigenvalue distribution is going to look like this. So it's going to follow this Marchenko-Pasteur law. Okay, and the observation is that after one gradient step on the first layer weights, well, most of the eigenvalues actually don't change. Okay, but you're going to have one additional eigenvalue, and this is precisely due to this additional low rank perturbation is precisely due to the gradient descent step. And the observation is that this outlier eigenvalue actually contains information of the single index target function. And so in other words, after one gradient step, your representation actually does give you the direction of the target function. And therefore, when you do ridge regression afterwards, you're going to get the prediction risk is going to be better than the random feature counterpart. Okay, so this is a summary of some prior results. And so now the question that we can ask is the following. So what if we don't have this non-degeneracy assumption, right? What if you do have what if you have this first derivative to be vanishing? Okay, so for example, if you think about the phase retrieval problem, okay, for phase retrieval, this sigma star is basically quadratic. So then it has vanishing first derivative in expectation. Okay, so what's going to happen here? Well, for that, we're going to introduce a Hermat expansion of the two nonlinearities. So recall that. So this argument inside of my nonlinearity, this was you can think of it as roughly a Gaussian, a standard Gaussian. So I can decompose the nonlinearity of the student, the neural network, and the target function in using the Hermite polynomials. Okay, so and I'm going to have a bunch of coefficients, alpha I and alpha I star. Okay, so these are the Hermite coefficients of the student and teacher model. So for simplicity, we're just going to remove the constant part. This is the part that's going to be the easiest to learn. You can just take the mean. And so under this decomposition, you can see that the non-degeneracy assumption, so here, this mu1 and mu1 star, they correspond to the first degree, these Hermite coefficients. Okay, so for this assumption to be satisfied, then I need alpha 1 and alpha 1 star to be non-zero. Okay, and why is that a useful? Why is this useful knowledge? Because so if we look at the gradient for the first gradient step on W, so intuitively it's going to be dominated. So we're going to initialize the neural network to be, so at initialization the neural network is somewhat small, so the initial output can be ignored. So if we ignore the initial output of the neural network, then the squared loss is going to be dominated by the correlation, okay, between the student and the teacher model. Okay, and this correlate, if you take the gradient of the correlation, then you get something like this. Okay, you're going to have the target f star multiplied by the derivative of the activation function, and there's going to be a by chain rule, you're going to have an input x. So this is what the gradient is going to look like. And by Stein's lemma, so you can actually pull out the direction of the target of single index target. And then this is going to be a scalar expectation to evaluate. And this expectation is simply the correlation between two single index model with, well, a different link function. And using this orthogonal, using the summated expansion, you can write this as a sum over this inner product. So if I'm computing the correlation between two single index model that points at different direction, so I should be able to write this as a sum over this the angle between the two directions, right? So so basically the gradient is going to look, the population gradient is going to look like this. Okay, and the observation is that because we do random initialization for W, so at initialization, these two vectors are going to be almost orthogonal to each other. Okay, so the typical case overlap between W and beta star at initialization is going to be something like d to the -1/2. Okay, and therefore, if I raise it to the ith power, the magnitude of this this term is going to be d to the -I divided by 2. Okay, so this is the expected. This is the rough magnitude of this term. Okay, so now you kind of see why what this assumption buys you, which is that so if alpha and alpha star is 0 for the first, say, like k degrees, then the first term that's non-vanishing in your gradient is going to have a magnitude of like d to the -k+1 divided by 2, which is very small. Okay, so in other words, so if the more zero coefficients you have in the beginning of this expansion, the smaller your expected gradient becomes. Okay, so this motivates us to introduce this definition. This comes from an earlier work from Benarouche et al. To introduce the definition of information exponent. Okay, so this is the smallest integer such that this alpha k star, this Hermite coefficient of your target function, is non-zero. Okay, so previously the prior results assume the information exponent is 1. Okay. So okay, and I'll give a few more examples of what this to hopefully to give more intuition of this definition. But roughly speaking, this kind of measures how much information is contained, like the magnitude of information in your gradient update. Okay, so for example, if if sigma star is just the degree 1 Hermite, so it's a linear function, then the information exponent is 1. Okay, if it's a pure degree 3 Hermite, then the information exponent is 3. The more interesting case is where you have a mixture of two Hermite polynomials. So if sigma star is the degree 1 plus the degree 3 Hermite, then the information exponent is still 1, okay, because this is the lowest degree. It's only the lowest degree that matters. Similarly, if I have Hermite 2 plus Hermite 3, then the information exponent is 2. Okay, so it's only, so basically here only the lowest non-zero degree matters. Okay? And the consequence is the following. So if I have a sigma star with information exponent k, then based on the previous calculation I showed, well, the population gradient is going to have a norm that becomes smaller as k become larger. Okay, because you have to raise this inner product w beta star to a higher power, and this inner product is vanishing at random initialization. So basically, for a function with high information exponent, the expected gradient becomes small. So now, to translate this to a sample complexity, we need to do gradient concentration. So the gradient concentration is going to look like something like d over n. Okay, but then because the expectation is smaller, then in order to achieve non-trivial concentration, you're going to need more samples. Okay, so because now this term has vanishing magnitude, and if you plug this expected magnitude into this d over n concentration rate, and you that what you see is that you need d to the k samples, okay, to non-trivially concentrate this vector. Okay. And that's precisely why we require k to be 1. We need this non-degeneracy assumption. So in order for the gradient to achieve sufficient concentration, when n and d are proportional to each other, well, I need this assumption. So this delineates the limitation of both. So for kernel model, as previously shown, you only learn linear functions. This is just bad. So if you do gradient descent on a two-layer neural network, well, you can learn nonlinear function. In fact, now the highest degree doesn't matter. It's but you need a non-vanishing sort of first derivative in order to achieve sufficient concentration in the proportional regime. So it only works when this information exponent is 1. Okay. I think I might pause for questions. Just okay, so I guess otherwise I'll keep going. So now the question that we hope to address here is, well, can we find settings where kernel ridge regression can learn something that's nonlinear, right? It's kind of underwhelming that you use a nonlinear model, but you ended up only learning a linear function. So can kernel model learn a function with higher degree, and can neural network similarly, if a neural network trained by gradient descent, well, can you learn it with can you learn something with larger information exponent in this proportional regime? Okay, so if you don't care about the proportional regime, here are the prior results. Okay, so for kernel, if you want to learn a degree p polynomial, well, you need d to the p sample. Okay. And for neural network, if you want gradient descent to succeed, then prior results show that, well, you need sort of d to the k samples in order to concentrate your gradient. Okay, so both of them will go beyond this proportional scaling for the degree for k or p that's greater than 2. Okay, so can we say something in this proportional scaling which kind of reflect this high dimensionality of your input of your training data? So now we have to cheat by introducing this spike covariance, right? So these prior results are for isotropic data. Okay, and so now by introducing this additional spike in this input data, so effectively I'm making the data more low dimensional. Okay, so in this case, there's hope that both kernel and neural network can learn a larger class of f star in the proportional regime. Okay, so this is going to be so this is the motivation of the study that we do. So we first consider this ideal setting, which is, so remember we have two directions that we care about. So one direction is the beta star. This is the target function. This is the target direction, and my input also contains a spike in some in the direction of mu. So in the most extreme, so in the most ideal case, I can assume these two directions overlap. Okay, so now this problem is quite easy. So I can directly solve it by first doing PCA and then learning my function on top of the leading principal component. Okay, so this should be the easiest problem. And intuitively, this kind of this is a setting where f star, your target function, focuses on the most prominent directions of the features. I guess the one way to motivate is that like MNIST is like 784 dimensional, but then if you do like kernel regression or linear regression on the top 10 or something principal component, you already get very good performance. So this is kind of saying that the target function actually looks at only your data is already your data already have low intrinsic dimensionality, and the target function looks at the leading components of the input features. Okay, so here the data is the spike covariance, and the spike points at the direction of beta star, which is precisely the direction of the target function. This is the most ideal setting. Of course, so if you know this a priori, then what you should do is like run PCA and then do learning. But of course, it's in reality, it's often so, especially for neural network, we don't do PCA. I think the hope is that by training the representation, it's like the gradient descent is going to do a PCA automatically for you in some extent. So the question that we ask is the following. So remember, so this theta controls how big of a low-dimensional signal I have. Okay, so larger theta means that I have a larger signal. Okay, so how large should we make theta in order for kernel models and neural network trained by gradient descent to learn f star? Okay, so that's the question we ask, and we want f star to be something that's nonlinear and something that was high information exponent. Okay, so let's look at the kernel result first. So for that, for kernel ridge regression, we have a precise characterization. So what we can say is the following. So if this signal to noise ratio scales with d to the gamma, for gamma that takes a value in this range, then the kernel ridge regression estimator can estimate precisely the first L degree, can learn precisely the first L degree of the target function. Okay, so this is sharp. So if you have gamma that's smaller, then you can only learn something that's less than this degree, and vice versa. So this is a sharp result. So the interpretation is the following. So if you plug in the degree of the target function, so let's say we want to learn a degree p target function, then the signal to noise ratio needs to scale with d to the 1 minus 1 over p. Okay, so this is a consequence of this of the theorem. So in other words, if I want to learn a linear function, p equals 1, then theta can take basically theta can be a constant. So this is consistent with what we previously see. So but if you want to learn a quadratic, if you want to learn a degree 2 target function, now theta, the signal to noise ratio, needs to scale with d to the 1/2. Okay, so now you need this input to be you need the input to be quite anisotropic in order to learn a higher degree function. And just intuitively speaking, the reason that you see this statement come from the fact that for the kernel method, the nonlinearity is applied to the inner product between x and xj. Okay, so between your training data, and this inner product is going to concentrate. So basically, when I is not equal to j, this inner product is going to be 0 with a fluctuation that's sort of like d to the minus 1/2. But then by introducing this low dimensional, this spike component, now you can sort of make this you can like now if you want to approximate this kernel matrix, then you will need a higher degree of Taylor expansion. Okay, so that's why you can so that's why the kernel intuitively can learn a higher degree function. So this is something that we can empirically verify. So here I'm plotting the dimensionality of in this heat map. So the x-axis is the dimensionality of the problem, and the y-axis is the signal to noise ratio, or the spike magnitude theta. Okay, and so and if the target function is degree 2, then as you can see, I have darker color means a smaller error. So when the spike magnitude scales with d to the 1/2, then I have learnability. Okay. And similarly, if I want to learn a degree 3 polynomial, then theta needs to scale with d to the 2/3. Okay. And this is consistent with this this lower bound we have. Okay. So this is for kernel methods. Let me check how much time I have. I have 20 minutes. Okay. So now for neural network, we have so the statement looked roughly it looks very similar. Here we do the difference is that here we do not have do not have a precise result. So we only prove a sufficient condition for gradient descent. So we have an upper bound. So what we show is that you can, if you want to learn f star with information exponent k, well, then the spike magnitude needs to scale with d to the 1 minus 1 over k. Okay, so this is exactly like the kernel result. So this for kernel, the spike scales with 1 minus 1 over p. Whereas here, so here you need to worry about the highest degree of the target function. Whereas for neural network, you only have to worry about the lowest non-zero degree. Okay, so again, so if you want to learn a function with information exponent k, then theta needs to scale with d to the 1/2. And if you want to learn a function with information exponent 3, then you get the scaling of d to the 2/3. Okay. So this is a sufficient condition, but in the experiment, we see that this seems to match this threshold seems to be sharp. Okay. So again, so from this, you can already see that neural network is going to give you some advantage, because this theta now does not depend on the highest degree. It only depends on the lowest degree. So if we compare them, okay, let me just go through the next slide first. So if we compare these two methods side by side, we're going to see the following. So remember, so k is the lowest non-zero degree in your in the Hermite expansion of your target function. P is the highest degree. So by definition, k is always less than or equal to p. Okay, so this means that unless your target function is a pure degree p Hermite polynomial, which is the case, for example, like here, p equals k equals 2. So in this case, neural network and kernel have the same scaling. Okay, but for all the other cases, so for when p is greater than k, then neural network will be able to learn this target function with a smaller signal to noise ratio. Okay, so here, when p equals 3, then kernel requires the theta to scale with d to the 2/3, whereas neural network can learn this function with a constant magnitude of spike. Whereas if now p equals 3, k equals 2, then the slope also differs, right? So for neural network, you have a d to the 1/2 slope, and for kernel, you have d to the 2/3. Okay, so basically, in most of the regime here, neural network can learn this target function more using a smaller signal to noise ratio or a smaller spike magnitude than kernel methods. Okay. So let me just quickly go over the intuition of this analysis. So remember that we're computing the magnitude of this population gradient before we do concentration. So just by Stein's lemma, what you see is that if you introduce a spike in your population, in your feature covariance, then if the spike points at the direction of the target function beta star, then this is actually going to amplify the gradient in this direction. Okay. So intuitively, so previously, so when theta equals 0, we have we get the expression for the isotropic data setting. But here, if I have if I have this additional rank 1 component, then the gradient magnitude is amplified by a factor of square root 1 over theta. Okay, and because of that, so now if I want to achieve non-trivial concentration in the Boltzmann regime, I just need to change, I just need to modify theta so that the expected gradient has non-vanishing magnitude. Okay, and that requires theta to scale with this quantity. So that's the intuition of why you can learn a higher information exponent function in using less samples. Okay, all right. Okay, so to sum up, so for the prior results, we assume the data is isotropic, and then there's a clear limitation of what kernels can do and what a neural network can do. Okay, whereas now if we introduce this anisotropic setting where the data already sort of reveals the low-dimensional target direction, then both kernel and neural network can do better. And we have this comparison. So if you for kernel methods, you need the spike theta to scale with d to the 1 minus 1 over p to learn this degree p polynomial, whereas for neural network, it's 1 minus 1 over k, where k is information exponent. So what this tells you is that if the data already contains some low-dimensional structure, then well, the performance of both kernel and neural network can improve significantly, but there will be a regime where neural network can learn the function, but kernel-rich regression cannot. Okay, so for the last 15 minutes, I'll just talk about one extension. So here we assume that the target function, the direction of the target function is already revealed in your data, in your input features. So this is a bit too ideal, right? So here, the right algorithm should be doing PZA first, actually. So what if you don't have this perfect alignment? Okay, so what if your data has is elongated in this direction mu, but then the target function points at some other direction. So target beta star does not perfectly overlap with mu. Okay, so now it's easy to see that if you do PCA, you don't get all the information of the target function. Okay, so now it's not clear what would be the best algorithm for this setting. But so I guess we might argue that this setting is slightly more realistic in the sense that it's saying that the F star is sort of partially captured by the large feature components, right? But there could also be some remaining components that are sort of distributed across the small features that are more difficult to learn. Okay, so the data. So here the data is still going to come from a spike covariance model, but the target function is going to it's not going to be perfectly aligned with this spike. So these two directions are different. Okay, and again, we're going to assume f star is degree p with information exponent k. Just a small remark. So this prefactor here is just to make sure that this argument inside of sigma star has unit L2 norm. So because this sigma star is from R to R, so this is just proper normalization. Okay, so to analyze this setting, then we need to keep track of two quantities, right? So previously we only have to analyze how theta, this spike magnitude, affects the learning performance. But now there's additional quantity here, which is the overlap. Okay, because beta star and mu, they come from different directions. Right? So then this overlap, the angle between mu and beta star is also going to affect how well the algorithm can learn this the single index target. So we keep track. So now we have two parameters that we can tune. So the spike magnitude is now, I'm going to denote this as gamma. This is gamma 2. This is the same as theta in the previous. It's previously, I think I use. Oh, actually, I didn't use this. Okay, but I think I previously used L for this. But yeah, so this parameter gamma tells you how large the spike in your input you have in your input features. And so larger gamma means that input data is more anisotropic. And now this new parameter gamma 1 tells you how well the spike in your input feature captures the information of the target function. Okay, so when gamma 1 equals 1, then if gamma 1 goes to 0, then you have perfect alignment. Okay, so then these two, then we go back to the previous setting. But then when gamma 1 goes to 1/2, then you basically have two random vectors. Right? So if you have two random vectors in high dimension, then this average, then on average, this inner product is going to be d to the minus 1/2. Okay, so that's why. So we take this, we take gamma 1 to be in the range of 0 to 1/2. Okay? So 0 is the most ideal case. You have perfect knowledge, and 1/2 is the case where the spike is pointing at some random direction. Okay, and gamma 2 similarly would take it from 0 to 1. So this is a new setting. Okay, so let's try to do the same analysis as before. So let's try to compute the one gradient descent step. And what you're going to see is that here, it's actually quite clear that one gradient step is not enough, in the sense that because now you have two directions. So there's so you have two spike directions, this mu and this beta star. So if you compute the first gradient step, what you're going to see is that the population gradient is going to be something like a linear combination of beta star and mu. Okay, so you don't get, so previously there's only, so both of them point at the same direction. So then the population gradient aligns with this target direction. But now it's going to be a linear combination of this beta star, which is what you want, and mu, which is the direction that the input features give you. But this is not the direction that you want to learn. Okay, so so one gradient step doesn't fully cannot give you the right direction for the single index target. But there's still some hope in the sense that, so because the gradient is in the linear combination of these two vectors, if these two vectors have a non-trivial alignment, okay, so remember, if these two vectors are kind of random, then this gamma 1 is going to be 1/2. So if gamma 1 is less than 1/2, that means the data contains some partial information of the target function. Then after taking one step, so just this linear combination of these two vectors are still going to bring me closer to to beta star than what I have in random initialization. So you can think of this, the first gradient step as providing like a kind of warm start, okay, to the subsequent gradient updates. So now, so our goal is to then analyze more than one gradient steps. Okay, so the first step kind of give you a warm start, but then so that means that intuitively, if you run more gradient step after that, the sample complexity should improve. Okay, so we want to study the sample complexity of this gradient descent, learning with gradient descent, and then the sample complexity should depend on these two parameters, gamma 1 and gamma 2. Okay, and so here, because we're running for more than one gradient step and there's these two parameters, actually we will not be restricting ourselves to the portion asymptotic limit. So we're running more than one gradient step. So the question we can ask is, well, what kind of gradient dynamics should we consider here? Okay, so the one candidate here. Okay, so for the purpose of this talk, let's just restrict ourselves to the dynamics of one neuron. Okay, let's assume that all the neurons of the pseudo model are just initialized in the same direction. So we're learning one neuron was one neuron. Okay, so this is a simple. So we're zooming into the training dynamics of just one neuron, and for this setting, the typical dynamics that people consider is a spherical gradient. Okay, so because the hope is the goal is to recover the direction of the target function first. So then, so spherical gradient doesn't optimize it doesn't care about the magnitude. You only so the hope is that you find WT that aligns with beta star, the true direction. Unfortunately, so for this, so prior works consider spherical gradient because the input is isotropic. But if the input is anisotropic, then there's actually it's quite possible that spherical gradient fails. Okay, and so we have this this little construction that even if you have this perfectly aligned setting, okay, even if mu gives you complete information of the target direction beta star, then the spherical gradient dynamics will still not be able to find this true direction. And this is actually very intuitive. The reason is the following. So because we are considering the squared loss. Okay. So remember the squared loss can be decomposed into, so this part is constant, I don't care. The squared loss can be decomposed into the correlation and correlation term, but there's also going to be a repulsion term. So in the sense that, so previously, if you consider the isotropic data setting, then this the L2 norm of fx, which is your pseudo model, is going to be constant, right? Because the W has unit norm. So this term is going to be constant. But now, because my data is anisotropic, as I rotate on the sphere, the L2 norm of the pseudo model is actually going to change. And in particular, if the direction, the target direction has some non-trivial alignment with the spike in the input, then when I get closer to the true direction, then this term actually becomes larger. Right. So because if my pseudo model moves towards, so when my student with W move towards the larger, towards the leading eigencomponent of my input features, then this fx square is going to increase. So this is actually giving you a repulsive force that prevents you from aligning with the true direction. Okay, so that's why. So for this anisotropic setting, if you do spherical gradient, you cannot recover the right direction. So what's the remedy for this? So one remedy is actually batch normalization, which is that so the intuition is that we want this term, or we want the correlation term, but we don't want the repulsive force term. So the simplest fix is just to normalize the pre-activation argument. Okay, so instead of looking at spherical gradient, we normalize the argument in the so here this inner product we divide it by the population covariance multiplied by WT. Okay, so this makes sure, so this ensures that the pre-activation always have constant magnitude. Okay, and this is kind of what batch normalization is doing. So you normalize this argument so that it doesn't blow up or vanish along the dynamics. So this is the right choice for the gradient dynamics is actually the normalized gradient here. Of course, here we require knowledge of the population covariance. But when you actually implement this algorithm, you replace it with empirical covariance. Okay, so you can estimate this from the batch. Okay, so now this is the algorithm. We do normalized gradient flow on the first layer. After that, we do the same ridge regression. Okay, okay, and so this is the sample complexity we get. I think so. This looks a bit okay. I think I will not go into the details for this slide, but I'll explain this theorem in the figures in the next slide. But basically, so we have two parameters, gamma 1 and gamma 2. So gamma 1 tells you the extent of alignment. Gamma 2 tells you the extent of anisotropy of the input features. So then the sample complexity for gradient-based learning is going to depend on the sample complexity is going to depend on these two parameters, gamma 1 and gamma 2. Okay, so there's going to be one regime actually where this additional anisotropy doesn't help you at all. You get so gamma 1, gamma 2 does not come into play. But then there's also going to be two regime where having this additional low-dimensional structure is going to help you. Okay, so let me illustrate this theorem in this figure. Okay, so this is the heat map for the sample complexity. Okay, so so first note that the regime where where this additional low-dimensional structure doesn't help is this lower triangle. Okay, so this is a regime where the sample complexity still scales with d to the k. And remember, this is the rate you get if your data is isotropic. Okay, so this is a hard regime where this gamma 1, gamma 2 doesn't give you anything. But also there's going to be an easy regime in the sense that so when gamma 1 goes to 0, that means I have perfect alignment. Okay, so if I have perfect alignment, so I'm looking at this. I'm looking at this side of the figure. So now the sample complexity, you're going to see a big improvement in the sample complexity, and this improvement is going to become more prominent as the spike become larger. Okay, this is when gamma 2 become large, then you're subtracting a larger constant, so the sample complexity decreases. Okay, and so on the other side, when gamma 1 go to 1/2, well, that means you have these mu and beta star. You can think of these as two random vectors drawn on a sphere. In this case, if the spike magnitude is large enough, you actually still get an improvement. Okay, so even if these two directions are kind of random, but if gamma 1 is sufficiently large, when the spike is large, then because of then the data still become more low-dimensional, and therefore the sample complexity can still improve. Okay, and then when gamma 2 goes to 1, that means the effective dimension of the problem is very low. So essentially the spike becomes so large that the problem is the features become almost one-dimensional. Okay, and therefore in this regime the sample complexity also improves. Okay, and then for any intermediate regime of this gamma 1, then as you increase the spike magnitude, you're going to get a better sample complexity. So intuitively speaking, so this is just saying that if you're not in this regime, so there's a hard regime where this low-dimensional structure doesn't give you anything. If you're not in this hard regime, then for everywhere else, if you have more alignment, then the sample complexity improves. And if you have a more prominent low-dimensional structure, if you have a larger spike, the sample complexity also improves. Okay, so this is what the theorem tells you. And finally, let's compare this again. So there's a kernel lower bound here, which is just come from a prior works that shows that any rotation invariant kernel is going to require something like 1 minus gamma 2 times p samples. Okay, so to learn this function. So again, this so we don't have to worry about this prefactor, but essentially this highest degree comes into play. Whereas for neural network, again, like only k, this lowest degree, matters. Okay, so this means that if k is small and p is large, then again we would expect neural network has a better sample complexity than kernel ridge regression. Okay, so let me sum up. So so for this talk, we're looking. So we studied single index model with anisotropic data, and then anisotropic data is described by the spike covariance structure. Okay, and we have the target direction is beta star, and this mu, which is the spike direction in the input, and so we characterize the sample complexity of neural network and kernel methods based on these two parameters, this alignment and the spike magnitude. And so in the perfect aligned setting, we have this precise analysis, and we also identified a regime where neural network works and kernel doesn't work. For the partially aligned setting, then there's actually a more complicated phase transition in the gradient descent dynamics, but here you need to run more than one gradient descent step, and the dynamics had to be the normalized gradient, so which resembles batch normalization. Okay, so I think that will be it. I think I'm right on time, but I'm happy to take questions.
Thanks, Denny, for the wonderful talk. You are right in time. So let me stop.